Okay, now we are at the final section, section D. Section D is very similar to section C, where we are going to transform the RLC circuit from time domain to S domain. The only difference here is we have initial conditions. Okay, so here we will see how to include the initial conditions inside the S domain. Okay, so the transformation of the source is exactly the same. For the RLC components, the resistor, there's no difference. There's no initial condition for resistor. So resistor is exactly the same. Inductors can store current and capacitors can store charges. Therefore, there can be some initial values. So how to include this initial current or the initial voltage of the capacitor inside the S domain? Okay, it's very straightforward. For inductor, as what we saw previously, in S domain, the inductor becomes SL and capacitor becomes 1 over SC. It is still the same. And then we include this initial condition as a secondary voltage source over here. Okay, so after the inductor, we just put a voltage source, and the value of the voltage source is L. L is the inductance of this inductor multiplied by I naught. I naught is the initial current. Okay. For capacitor, it's the same thing. We put a secondary voltage here, and the value here is V naught over S. So the V naught will be given to you, just V naught over S. Okay, one more important thing to notice over here is the polarity. For inductor, the polarity is such that it is negative where the current enters. Okay, so you can just check where the current enters, make it negative, and the other side is positive. For capacitor, this secondary voltage source here, the polarity is positive where the current enters. Okay, so I will redraw it here. For inductor, we just put this. This becomes SL in the S domain, and then you have a voltage source, and the value is L I naught. Okay, and since current is flowing in this direction, this is negative, this is positive. For capacitor, so this is 1 over SC, and then we have a voltage source here, and the value is V naught over S, and V naught is the initial value which is given to us. Okay, and since current is flowing here, it's positive and then negative. Okay, so that's all. That's all the way we transform the circuit. Okay, and note that if the I naught is 0, then this becomes 0. You don't need to put this. This is similar to with no initial condition. You don't need to include the secondary voltage. Okay, now let's look at an example. This is the similar example as previously, but now we have an initial condition here. So when we have an initial condition, okay, here I've regenerated the circuit, reproduced the circuit here. Let's transform the circuit. Okay, we draw the circuit. First is the source, and then we have the resistor, and then we have the inductor. Okay, exactly the same. But since there's an initial condition, we put a secondary voltage source after the inductor. Okay, now let's determine the values. So the source becomes 50 over S. Resistor is still the same, 10. So 10. Inductor becomes 1 times S. So this becomes 1 times S. I'm just going to put a S. And for current is flowing in this direction, IS. So for inductor, as what we saw previously, where the current should be negative and this should be positive. So we have determined the polarity. And finally, we determine the voltage over here. The voltage here is given by, we refer to the slide, L I naught. So we take the L. L is L I. This is the voltage. This voltage. So L is 1. I naught is given as 1. So 1 times 1 is 1. So this is 1 volt. Okay. So this is the diagram over here. Okay. Next step is we want to find the transfer function Is of Is. Again, we just apply the Ohm's law. Is equals to Ohm's law. We add all the source voltage source. So this is 50 over S. Okay, and then this voltage, since current is entering the negative terminal, it should be plus 1. Okay, so for source, current enters the negative terminal and exits from the current uh, comes out from the positive terminal and enters the negative terminal. So we put plus 1, and if this is positive, then we put minus 1. Okay, and then divide by the total impedance. So the total impedance is just 10 plus S. Okay, so that's all the um, transform for this circuit for the Is. Okay, if you want, we can further simplify it by multiplying the numerator and denominator by S, and we'll get this more elegant expression. Okay. So thank you. That's all for section